some questions that people gave me emails. I want to address those first. They might be some of your same questions too. So first of all, on the tutor assignment for magnetism, there were questions about 12, 15, and 18. And you know that, oh wait, 12 is actually this one, right? Oh, my numbering is different.
Yeah, I think it is. I remember I was looking at that one too. That's on 12.
10, and then that's 11. Yeah, so this one, this number, this is really your number 12. In a long straight wire, what current is required to exert a 1 micronewton force on a 1 microcoulomb charge moving at that speed parallel to the wire a distance of 0.35 meters? So there are a couple of things that you have to do here. You have to know that F is equal to QVB, right? Because I'm looking for, QVB, and then also that the magnetic field due to this wire is equal to mu naught I over 2 pi R. And so I have a wire, and then there's a certain magnetic field right here, and then there is a charge coming in with a certain velocity, and it enters that magnetic field, and I want to know what current in the wire will produce a magnetic field that produces the force on that charge. You follow me? You with me? Okay, so I can take this and plug it in for B right here, and I get F is equal to QV mu naught I over 2 pi R. And then I can solve for I, which is what I'm looking for. So that's F, which are F 2 pi R divided by Q V mu naught. And so that's F is going to be 1 micronewton, 1 times 10 to the minus 6 newtons. 2 pi R is the distance from the wire, that's 0.35 meters, divided by Q, which is a 1 microcoulomb, 1 times 10 to the minus 6 coulombs. V is given 1.5 times 10 to the 6th times mu naught, which is 4 pi times 10 to the minus 7. And then I can cancel out some things. That cancels with that. The pi cancels there. I can cancel this and make that a 2. And then that should give me the answer, 0.35 divided by 1.5 e to the 6th divided by 2 e to the minus 7. I get 1.16, 1.2 amps. Okay? All right, number 12, also number 15, which is actually my number 14. Okay, so we've done them like this before, but it's still good. You might see something like this on the test. I'm calling this number 15. This is your number on it. And I want to know if I have a current in a wire and I have a positive charge that goes like that, what is the direction of the current? So two-step problem. First I need to figure out what's the direction of the magnetic field that caused this. So I'm going to simplify it a little bit. I have a velocity in this direction and a force in this direction. These vectors describe the velocity and force on this particle. So if I have a velocity to the right, a force up, that means my magnetic field is into the page. So my magnetic field here is into the page, and that means magnetic field into the page, out of the page on this wire. In order to get that, what's that? A down current. So my current is down on that one. Okay, we good? All good? You can stop me if not. And then number 18, which is actually number 17 here. Oh yeah, so this was several people had issues with this. If I have a hot and a neutral wire, let's draw the neutral black. So this is my hot wire, and this is my neutral wire. The issue is, why is it repulsive? Because people were assuming that the current is in the same direction on these, but that's not true. What you got is you have a train car that's traveling on these two rails, and you get a current that flows from the hot wire, flows across the train car, and then it flows to the neutral wire. So you actually get a big loop of current, and then when you have two wires with currents that are in opposite directions, like this, and as you know, those are going to feel a repulsive force. If they're in the same direction, they feel an attractive force. So that's why it's repulsive and not attractive, because you actually get a big loop of current going, but you don't get current going in the same directions. That wouldn't work for the train. It wouldn't provide any power to the train. Okay? We can come back to these. Let me get all the ones that students asked offline. The other was RC circuits on Tutor. That was back in March, I think. Yeah, and they had asked about number 3. Oh yeah, I had several people ask about this one too. Uncharged capacitor is connected to a resistor. I want to know, how long does it take to have half its maximum charge? And it looks like it's charging, right? It's a charging capacitor. So for charging capacitors, Q is equal to big Q times, let's see, what is it for charging? It's the 1 minus bit, right? 1 minus e to the minus t over RC. And I'm told that Q over Q is equal to 1/2, because I want to know, how long does it take the capacitor to get half its maximum charge. So little q is half of big Q. That means Q over big Q is 1/2. And then that's equal to 1 minus e to the minus t over RC. So I have negative 1/2 equals negative e to the minus t over RC. Those go away, and then I can do a natural log of both sides. And this is, watch carefully, this gets rid of this, and I get natural log of 1/2 equals negative t over RC. But if I take the negative of both sides, and this was the step that most people messed up, and for good reason, we didn't actually talk about this with the exponentials, but the negative of natural log of 1/2 is natural log of 2. So that's where that comes from. I sort of blame myself, but nobody asked either about what happens with that negative. No. Okay? And then somebody asked about images. About, for example, they asked in particular about the fish problem or the star problem. Like, if you look at one of these, where is the actual image formed? And the way that you determine where the image form is you draw a ray up, and you know it's going to bend away from the normal, like that. And then to find out where the image is, you trace the refracted ray back. And so I'll trace this ray back, and so my image in this case is right here. Or you could think of the image as being right here. It doesn't really matter. The image is going to be along that ray that the person is actually seeing. And so that was true in the fish problem, and it's also true in this one. Okay? Is that clear? Okay, let me try again. So there are light rays coming off of this object, and those light rays are the rays that you see. The light rays, however, they come off, they're going to bend away from the normal. I'll have other light rays that'll come off, and go in different directions. Like I'll have a light ray that will come here and it'll bend in that direction, but that's not the light ray that the person sees, right? Because it just doesn't go to the person's eye. But when the person sees this light ray coming to their eye, the mind doesn't think, oh, the light has bent. And so it just says the object is along that light ray. That's where it sees the image of the object. Okay? All right. Somebody else asked about B and E fields. Let's just do an example. A couple rules you need to remember: that positive charges feel a force in the direction of the E field. That's from chapter 2. Negative charges feel a force opposite the direction of the E field. So for example, if I have an E field that is in this direction, and I have a velocity, a positive charge, with a velocity in that direction, that charge, when it enters into that electric field, is going to go up like that, because it has this upward force that's pulling up on it. However, I want to be able to create a magnetic field that will directly counteract or counterbalance that electric force. So if I draw my force vectors, Fe is in this direction, I want to create a magnetic field so that my magnetic force is in the opposite direction. And then that will allow the charge to travel through this electric field and the magnetic field without any deflection at all. It's quite common to have magnetic and electric fields together in certain devices like mass spectrometers, for example, or in various types of like cathode ray tubes or TVs, but you use them for other instruments too, where you're directing a beam of electrons or charged particles to where you want them to go. So here, the question would be, what is the magnetic field? And I could ask you, what is the magnitude of the magnetic field, or what is the direction of the magnetic field? To find the magnitude of the magnetic field, I would say Fe has to equal to Fb. That's QE equals QVB. And I would solve for B. You had to do that. So B is equal to, what, E over V. Or I could solve for V. V is equal to E over B. Also, I could ask you, what is the direction? These are all good questions, by the way, so they're good questions for you to practice for your test. I could ask you for the direction. I would have a velocity that's in that direction, a force, that's my magnetic force in that direction. That gives me a magnetic field that is out of the page. So I would have to have a magnetic field in concert with this electric field out of the page that will cause the particle to go undeflected through both. Both of those are reasonable questions for the test. So it's your right-hand rule here. V, F is down, so I know my thumb goes down, and then my magnetic field comes out of my palm. Okay, and then finally, somebody just wanted to reaffirm that they know how to solve this exponential, because as you know, that is on the free response, so it's worth quite a bit. For this in particular, Q1 minus e to the minus t over RC. When I'm solving this, the first thing that I do is I divide both sides by Q. So I get Q over Q equals 1 minus e to the minus t over RC. And I want to get that exponential all by itself. So, I subtract 1 from both sides. So I get negative 1 plus Q over Q equals to negative e to the minus t over RC. And then I would take the negative of both sides, so this would become positive. I would negate this, whatever number that is. Most of you will probably sort of do this piecemeal, putting in the numbers. That's usually how students do it. And then I would take the natural log of both sides. So I would take the natural log of this, that gets rid of the exponential, and the natural log of this side. And I would get, gosh, whatever number that is, natural log of 1 plus q over big Q is equal to negative t over RC. And then if I'm looking for t, I multiply both sides by negative RC.
Would it be minus Q over Q?
Yes, you're right. Thank you. Okay? That looks complicated. Usually students put in numbers and it goes a little more quickly than that. It's not that complicated. Okay? Y'all can do that? You'll have to do it tomorrow.
The minus RC like on the right side of the equation.
Huh? Yeah. I'm not subtracting, I'm multiplying.
Oh, okay.
Yeah.
That would just cancel.
Yeah, it would just cancel here and make that positive and just leave you with t. All right? Remember, there are 3 questions on the free response. There is there's charging, discharging. And then there are parts to that. What is t equal to? What is tau equal to? What is the time for full charge or discharge? I'm just going to say time for full. And then I want you to draw the graph, either like this or like that. Okay, so that's 4. That's half of your free response, because remember there are 8 total. What was the second one? Oh yeah, I forget, what did I tell y'all? Were there just 2 parts here? Yeah, it was just like having a charge moving into a magnetic field of some sort. I may or may not give you the direction of the magnetic field. I might give you the force instead. We've done something like that. And you have to do something where you do this QV over MB, isn't that right? I think that's right. Where you're using that equation to figure out, RV or B, RM over Q, the mass to charge ratio. Yeah, Cam? Did I get that wrong? I'm sorry, I can't remember all that stuff. MV over QB. Okay? And then also the second part of that would have to do with the direction. And then, so that's 4, 5, 6 parts. And then the 7th part, as I told you, would be on refraction. I'd give you something that looks like this. I'll give you this angle, say, I don't know, 30 degrees or whatever. I don't think it's 30, but whatever it is. And I ask you for what is the angle, the refracted angle here. Okay, where you say n1 sine theta 1 equals n3 sine theta 3, using your law of refraction. But then I also want to know, does it bend towards or away from the normal? And I'll have some words you circle, towards, away, towards, away. You'll just do it twice. And it'll be dependent upon, are you moving from high to low or low to high index of refraction? We can look at that if you're confused about that. So 2 things, how does the light ray bend? And then what is the refracted angle in that third medium? Okay? All right. All those are great questions, and some of y'all actually asked those questions, but other students have too. What are particular questions that y'all want to look at today? Okay. Yeah. So solenoids. I'm going to pull up the old test, but then we'll. Hey, look, it's me. There's solenoid in this one. Is this 17? Okay, so with solenoids, like number 8 here, We did this one in class actually, but you can see solenoids in a couple of different ways. Like you can see a solenoid if it's face on like this. This is a little easier. This is like you're looking down the end of that tube on the right, and I would give you the direction of it, of the current, and I could ask you one of two questions. I could ask you, what is the direction of the magnetic field? And with a solenoid, it's always the direction in the middle of the solenoid. I'll make that clear. But you use your right-hand rule. Remember the three applications of the right-hand rule? The first two are identical. The third is a little bit different. Thumb in the direction of the current, fingers wrap around. Here, thumb in the direction of the current. If I do the bottom, it'll look like this. And so that means it goes into the page in the middle, and then out of the page on the bottom. And then that's actually true all the way around. So that would be one question that I could ask. The other question I would ask is, what is the magnetic field right there in the middle? And B in the middle is equal to N mu naught I over 2R. This is on your equation sheet. Remember, be careful, because you'll probably have to use both equations. One has a pi, but without the N, and then the other has the N, but without the pi. N is always a solenoid, because solenoids usually have multiple terms. That's really all I can ask, just those two. All right, so right-hand rule, and then just knowing which is the right equation, and realizing what those are. N is the number of turns, mu naught is your permeability of free space, and I is your current, and R is the radius of that coil. Okay? Is that clear? Is it clear? Oh, you're doing right-hand rule. I thought you were waiting. Okay, what else? Yeah. Yeah, so remember with the right-hand rule, that third application, if I have a current going in that direction, for example, I'll let my thumb go in the direction of the current, and then my fingers wrap around. So here, I like to think of it as I take my pencil, my fingers wrap around, so they go into the page, out of the page, like this. Likewise, if it's like this, I do the same thing. So my magnetic field goes like that. Okay? So here, it's going to go into the page, out of the page. And now I just apply this to the coil, but just to a little section. So I'm just going to pick this little section. And so if you imagine this wire, you just rotate it around like this, and I'll get into the page right here, and then out of the page down here. But then as I move around, see now the current's going up, into the page, out of the page. If I do that all the way around the coil, I get the same magnetic field generated by each section of the coil. Okay, is that clear? Yeah. What else? Want to just look through some of the old tests and take a little look-see? All right, let's start with this one. This one's fine. This is spring 16. You know, there's some, let's see. Your test will actually pick up with RC circuits and household circuits. So make sure you understand those safety features that you use in a household circuit, how to find the power, particularly the total current that is listed on the circuit breakers. We worked a problem like that. And what those various safety features do. And then the RC circuits, make sure you know how to calculate the charge, current, or voltage at a particular time. You could see that not only, you will see it in the free response, but you could see it also in the multiple choice questions. They'll be simpler as far as how you do the numbers, but you can still see them. And then moving into chapter 5, that's where it picks up here. So this is, you know, the F equal QVB thing, number 1. Need to know your basic stuff about magnetic forces and magnetic fields, magnetic domains, the magnetic field of the Earth. This is a right-hand rule. This is the E and B fields. This is finding the magnetic field due to a long straight wire. That's that mu naught I over 2 pi r. Really, it's just knowing the formula and what they mean. There's some stuff about magnetic fields, solenoids, right-hand rule. Y'all stop me if anything pops out at you. That's, on this test at least, that's it for chapter 5. And then moving into chapter 6, know your electromagnetic spectrum, know your history of light, know your reflection. You will see a problem like this. Number 14? Sure. So with number 14, I have a light ray that comes in at 40 degrees, and then it reflects at 40 degrees. So I know this angle has to be 50 degrees because this is a right angle right here. And so those two angles have to add up to equal to 90. I'm told that this angle is 100 degrees. That means that this angle has to be 30 degrees. And if that angle is 30 degrees, this angle is 60 degrees, and so this angle is 60 degrees. So the answer to this one is 60 degrees, A. Three things you need to know. The law of reflection. You need to know that triangles have 180 degrees. That was relevant with this little triangle right here. And you need to know that the sum of these two angles is equal to 90. You will have a problem. It'll be just like that, except, different angles. So if you can't do it, make sure that you can do it by tomorrow. Okay? You'll see, you're definitely going to see something like this, where I just ask you, what is the angle of refraction? Or I might give you the angles and ask you to find the index of refraction. So using Snell's law to calculate n theta 1 or theta 2. And then likely you'll have something like this where I show you how light bends, and I'll ask you something about the indices of refraction or the speeds of light in that medium. You will have a question like that. All of these things you'll have. You'll probably have to calculate the speed of light. I don't remember if I put that in there. Yeah?
Is there going to be a mass per charge question for the spectrometer?
Probably so, yeah. That is in one of my big categories of questions, so they almost always make it in. You have fewer multiple choice now, so sometimes things get left out, but I'm pretty sure there's at least one like that. Okay? Don't forget, you will have a total internal reflection, pretty sure. Where you have to calculate the critical angle or describe the relationship between the two indices of refraction required for total internal reflection. Remember, big index in the middle, low index on the outside. I always think of those fiber optic cables you can buy at like those like gag shops or whatever, you know what I'm talking about? They're always plastic surrounded by air. The plastic is a high index of refraction, that's the actual fiber, and then they're surrounded by air, which has a low index of refraction. Y'all might not go to those places. Okay? You want to look at some other, any here you want to work? Y'all just got it? You feel okay? Yeah? I don't think it's that hard, actually. I just finished it this afternoon. It was probably harder to write than for y'all to work it. Okay, so this is a good one, Spring 17, because it starts up with household circuits and it goes all the way through all of our stuff. So what's constant about the appliances, just sort of basic stuff. You're probably going to have a question like this with circuit breakers. And, on these, I know that P equals VI. So if I want to find the current, that's going to be equal to P divided by V. So for example, my 1200 watt heater divided by 120 volts, that's equal to 10 amps. And I usually try to give the power so that it divides evenly. So 240 watts is 2 amps, 360 watts is 3 amps, 480 watts is 4 amps. Okay? And then you're figuring out how many of those devices will take me up to but not over the circuit breaker switch. Because if you go over, then it kicks off, right? You want to get under the 15 or the 20 amps or whatever is allowed.
That's the type of question you meant by whenever you said that you need to know the power and total current.
Yeah, that's what I meant. Yeah. And you do have a question. It's not exactly like this, but if you can do this one, you should be okay with that one too, okay? Just general stuff about household circuits. Make sure you know the difference between GFI or GFCI and circuit breaker. People often get those mixed up. GFCI will always have an inequality in it. Right? That IN is greater than I out, right? Because if I out is small, that means you're losing current somewhere. And then circuit breakers are just, is I bigger than some value? I guess they both have an inequality. But the GFCI is comparing two currents, and the circuit breaker is comparing a current to a set value. And then also your grounding is to ground your devices. That's to protect you from faulty devices. The ground, right, that's its primary purpose, is to protect you from faulty devices. Whereas the other things aren't really for that. The other things are for protecting you in other ways. But the grounding is particularly to protect you from faulty devices, not the other things. Did you hear what I said? Okay. You have to do this on the free response, but you know, B is for a charging and A is for a discharging. Just know what the functions look like. The B option here is the 1 minus e to the minus t over RC, and the A option is the e to the minus t over RC. That exponential function always goes to 0. And so if it's just e to the minus t over RC, that means your whole function is going to go to 0. But if it's 1 minus that, then it means it's going to approach 1, or your maximum value.
It's always going to be like the
Yeah, isn't that right? Current, yeah, current will always decline. You can go to your equation sheet. That's really what you want to go off of for those. Where is it? I did send out the equation sheet, and I realized later that there's one thing that's not on there, and that's this equation right here. But I can give that to y'all in class tomorrow. Y'all saw the equation sheet that I sent you? Yeah, that's what you're gonna. I'm just trying to save some paper. So yeah, so this, for example, the charging, that is a growth function, right? That looks like this. Whereas this discharging function right here, that's the declining function that looks like that, the decay function. But yeah, right, current is both ways. So charging or discharging, it's going to be a decay function. And the reason is that, you know, initially when you're charging a capacitor, you get a big burst of current, and then it says, oh, I don't need that much current now, so it declines as you get more and more charge on the capacitor. And then similarly, when you're discharging the capacitor, you get a big burst of current right at first, but then it declines because, well, I just don't have as much charge anymore, so my current declines or decays. Okay? Make sure you're familiar with what's on here. Look, there's your solenoid. It doesn't say solenoid, but I know it is because it has 10,000 turns of wire. Want to know the magnetic field. Here's your F equal QVB. Stuff about magnetic force. Remember, magnetic force is a centripetal force. It's always perpendicular to the velocity. It cannot change the energy of a particle. Centripetal forces don't do that. They only change the direction. This is the right-hand rule. That's our third application. Electromagnetic spectrum. Magnetic fields run north to south. And then light stuff here. Calculating the speed of light. The speed of light, that's V. So it's what? C divided by N. N is always bigger than 1. Don't forget that, okay? Our index of refraction. The way we do that, since the speed of light can never exceed C, that means that N is always bigger than 1. Bigger than or equal to. In a vacuum, it's equal to 1. Okay? Remember I told you you'll have one like this. I don't know if you have a ranking, but you certainly do need to know, be able to discern between high and low speed or high and low index of refraction. Remember, they're inversely related. So if I have a big speed, that means I have a low index of refraction. We'd stop there at 23. Okay? More questions, or are we feeling okay? Feeling okay? more questions then? Yeah, I'm going to stop this. If you have, I have a few